Dear ladies and sirs, my name is Claudia Toledo. With this project, we want to improve the way we inhabit the Amazon region of Ecuador, in harmony with nature. We are students from Universidad Tecnológica Indoamérica, located in Ecuador, and we present you now Funnel House. Funnel House is located in Ecuador, in the Amazon region, Napo Province, Tena Canton, Pano Parish. The lot is located 4 kilometers away from Pano Town and 4 kilometers away from Tena City, right in the middle of both. This project enjoys a privileged location, surrounded by one of the richest ecosystems on our planet, the Amazon rainforest. The importance of this ecosystem has led us to think more closely about the environmental impact that the construction industry can have. The borders of the Amazon are inhabited, with growing cities in the middle of nature. It is very important for our future to establish a sustainable relationship with the urbanized regions of the Amazon, to guarantee the protection of its natural regions. Tena Canton is made up of one urban parish, also called Tena, and 6 rural parishes. Our project is located in Pano, rural parish. Tena Canton has approximately 60,880 inhabitants and a population density of 234 inhabitants per square mile, and a surface of 1,507 square miles. Population settlements are scattered and small, settled mainly along the banks of the Napo River and on the outskirts of the urban parish of Tena. Its economic structure is based on agriculture. In the image, we can appreciate the city of Tena, crossed by the Napo River. The population in Pano is mostly young. Around 80% of the people are between 15 and 45 years old, being an important potential client for housing. The families are patrilocal, meaning that the wife moves into the husband's parents' house and is considered a part of that family. For this reason, our project has a progressive growth potential. More than half of the families in the sector own a house, for 3 to 4 dwellers, which represents a significant market potential for our design and an important chance for its replicability. The following image shows an average house in Pano. 81% of the roofs are made of zinc plates, and 78% of the constructions are made of wood. The cost of this 102,000 square feet house ranges its price from $36,000 to $48,000. We should consider that this type of house does not meet the environmental quality and comfort standards. Our team carried out 80 surveys with potential clients in the project's area. It was determined that the majority of the potential clients, 65%, are willing to pay between $70,000 and $110,000 for a 1,689 square feet house, the size of our project. After the analysis, it was concluded that an average dwelling in Pano does not meet the needs and characteristics of its clients. Also, our potential clients are willing to pay more for a house with better conditions. A detailed budget calculation of our project was performed, establishing a final cost of $62,811 $37.2 per square feet. This includes lot, labor, construction, machinery, appliances, and material costs, shown in the points 1 to 6. The design process included 4 phases. First, the environmental and user conditions were analyzed. In the second phase, passive strategies such as morphology and orientation were optimized to achieve the desired comfort. third phase included technologies analysis and implementation to improve environmental quality and comfort. Finally, a coherent architectural expressiveness was defined, mixing vernacular and contemporary architecture. Environmental conditions are crucial for making decisions. The maximum temperature of this parish is 89.6 Fahrenheit degrees and the minimum 57.2. Humidity can reach 81 to 92%. The maximum precipitation level is 38,553.1 millimeters. The months with the most cloudiness are February and July, and the ones with the most hours of sunshine per day are July and August. The conclusion was that the building needs to be cooled down and the relative humidity needs to be lowered. Funnel house has an elongated form to reduce solar exposure from east and west. Its form also optimizes the capture of the south prevailing winds to maximize natural ventilation. The architecture program was divided into open spaces with permanent natural ventilation and closed private spaces with mechanically improved comfort. The project was modulated to allow progressive growth. In Ecuador, the sun reaches an inclination of 23.4 degrees during the solstices. The north and south walls were tilted at this angle to avoid sun incidence and decrease thermal gains. The other walls were also tilted to avoid the sun from east and west. The hotspots like kitchen, shower, and machinery room were unified into one model, separated from the others, to be ventilated and avoid heat transfer. Finally, the building was raised from the ground to allow circulation under it, avoid possible floods, and prevent the entry of wild animals. The original vernacular architecture of the Ecuadorian Amazon region is being left behind due to immigration from the Ecuadorian Andes cities that brings different construction techniques which do not respond to its environment. Funnel House deeply analyzes the knowledge of vernacular architecture accumulated for generations, mixing it with modern techniques, technology, and contemporary architecture. The local vernacular architecture divides the house into two main parts: the ekent, or private area in the native Quechua language, and the tankamash, or public social area, separated by the taned, or bunk beds. It can be seen in the left diagram. Vernacular houses are built with local materials, such as natural fibers, palm leaves, bamboo, and chonto wood. The wall layers are placed vertically outwards and horizontally inwards, separated from each other to allow natural ventilation. Our project takes this idea of distribution and reinterprets it, as can be seen in the diagram on the right. In this way, its functionality adapts to the customs of the inhabitants of this region. Funnel House reinterprets the strategies developed by vernacular architecture. The house is divided into three modules, connected by a semi-open hall that includes circulation and social spaces. This hall also interacts with the gardens that help to regulate temperature and bring nature closer. The first module includes the living and dining room, located in two separate spaces that can be arranged into one to host social events. In the second module, we find the kitchen, bathroom, and machinery room. Finally, bedrooms are located in the third module, each one equipped with built-in wardrobes and storage, and hammocks in the semi-open hall. The design, ergonomics, and accessibility meet local and international standards, providing an excellent occupant's experience and comfort. Each module comprises two areas, a public area in the semi-open hall and private closed areas, isolated with several control layers to guarantee its comfort. The walls inclinated to avoid solar radiation also help to accommodate the storage spaces. Funnel House offers the highest life quality for its occupants. We used the International Well Building Institute certification as a guide, analyzing 10 parameters. These parameters will be explained in the following sections. In order to reduce the energy consumption of the house, the project implements several passive strategies to maximize cooling. 1. The building is lifted from the ground to allow air circulation under the floor, cooling it down in the shadow. 2. The air carried by prevailing south winds is cooled down as it passes through vegetation. 3. Different vertical distances at the entrance and exits of air accelerate its circulation, improving natural ventilation. 4. Rain protection was carefully designed, allowing also rainwater collection on an underground tank for reuse. 5. The maximum sun inclination was used to calculate the inclination of the walls and the roof's eaves to prevent thermal gains due to solar radiation. 6. Cold air regulators on the ground floor allowed the entry of cool air circulating under the building. 7. Native trees surround the building to increase shading and air cooling. 8. The windows are designed to allow natural ventilation. They include anti-bug nets. A mechanical ventilation system is implemented to reach the goal on thermal comfort. Due to the high relative humidity of Pano Parish, the mechanical system allows ventilation with variable flows depending on the humidity rate. This guarantees an appropriate quality of the internal air. The following strategies have been implemented. 1. Private spaces are isolated for better performance of mechanical systems. The windows close hermetically. 2. Outdoor air collectors introduced to mechanical systems. 3. A drive grill distributes purified air into the isolated spaces. 4. A self-regulating grill extracts stale air from the isolated spaces. 5. The semi-open hall operates with permanent natural ventilation. The main challenge regarding thermal comfort for this project was the high temperatures and high relative humidity of Pano Parish. This solar analysis was very important to reduce its incidence on walls and indoor spaces. The wall inclination and roof eaves provide solar protection through the year to reduce thermal gains. Funnel House generates more energy than it consumes. Ecuador has a very constant solar irradiation throughout the year due to its location in the planet, with similar solar inclinations to the north and south. This house uses only electric energy, generated by 10 photovoltaic panels that produce 508,007 kilowatts per year. Its energy consumption is 4,338 kilowatts per year, having an energy surplus of 1,469 kilowatts per year, which is returned to the grid to compensate the energy consumed during the night. G3M Company was a key partner to design this real market system. The panels are equally distributed in the two roofs over the central module, with a seamless integration. The panels have an ideal 20% inclination to maximize energy production, which also allow self-cleaning by the rain. The graphic shows the energy simulation results using Design Builder. Thanks to the passive ventilation systems used, it was possible to lower the energy consumption needed to guarantee thermal comfort for our users. This way, we avoided the use of air conditioning systems, which are very common in this context. The highest consumption is made by the hot water system. The desired thermal comfort inside the dwelling was defined to meet ASHRAE Standard 55. In this simulation, it can be seen that an optimal operating temperature of 77.7 Fahrenheit degrees is maintained inside the home, with a relative humidity of 67.04%. Even though artificial illumination represented a very low energy consumption compared to the other systems, it was also studied to provide natural illumination for all the spaces during the night, meeting the optimal values demanded by local standards as seen in the right chart. The house allows indirect daylight to enter spaces through windows and blinds. The semi-open hall is illuminated and protected from radiation using blinds placed at 30 degrees, which provide natural light and ventilation while avoiding solar radiation and rains. Pano Parish is exposed to different risks produced by nature and human activities. Resilience strategies were implemented to address each potential risk. The structural design is flexible and resistant towards earthquakes. In case of isolation due to pandemics, social disturbances, or others, the social spaces allow different uses, and the gardens include food production and rainwater reuse. The house rises 3 feet above the ground level to prevent damage in case of flooding, and the lot is located away from the Pano River flooding zone. The roof system allows water to be evacuated effectively in response to heavy rains. The house is built over improved soil and has a continuous reinforced concrete foundation that gives stability to the land and the house. The presence of insects, amphibians, and small reptiles is very common in the Amazon settlements. The rise of the building above the ground level and the use of anti-bug layers keep these unwanted guests away. Deforestation is avoided by using certified construction woods, obtained from environmentally responsible cultivations. Funnel House effectively integrates high-performance engineering systems and building science practices to achieve efficiency. The house has a continuous concrete foundation with steel reinforcements. The building implements a bamboo exostructure that supports the roof and the interior spaces. Secondary structures form the walls, floor, and ceiling. Windows have their own system to be hermetic. Bamboo or Guadua angustifolia has its own construction regulation in Ecuador, which explains the extraction process, treatment, and detailed construction techniques. The private closed spaces use an HVAC system, implemented to reduce relative humidity and ensure internal comfort, with lower energy consumption compared to the common systems used in this region. A dual-flow controlled mechanical ventilation system is used. It is made up of two subsystems, the drive system and the extraction system. The house uses 10 photovoltaic panels located on the roof, connected to an inverter and control board, powering the house for appliances, illumination, and ventilation equipment. The appliances and equipment were carefully selected to be energy efficient and available in the local market. The sanitary hot water is produced by a thermosiphon system with a 4-step operation. The collectors catch solar radiation. Then the solar radiation is transformed into useful heat, which is used to heat a fluid. Finally, the fluid heats the water contained in the accumulation tank. A thoughtful water system provides autonomy and allows water reuse. The local drinking water grid supplies the house and fills the reserve tank for 5 to 7 days in case of an outage. Rainwater and grey waters are recovered, treated and reused in the toilet and for gardens irrigation. The black waters are treated using a biodigester septic tank. The house has different control layers of protection, complying with the building science fundamentals. Walls, floors, and ceilings include a vapor-resistant layer made of polyurethane foam applied to OSB panels. Walls and floors are filled with palm fiber for thermal and acoustic insulation. The roof is made of a galvanized sandwich panel with polyurethane filling that provides thermal and acoustic insulation. The wall's inclination prevents from water filtrations. They finish with 2 layers of water-resistant stucco, white-colored on the outside to reduce thermal gains. The spaces and windows are closed hermetically to prevent air leaks. As you can see, the house is built with Ecuadorian materials and labor. The natural palm fiber used as insulation proved to have better insulation conditions than synthetic materials such as fiberglass or fiber rock. Funnel House ensures efficiency in maintenance, reducing costs, time, resources, and environmental impact. The proper materials treatment prolongs their lifetime. It uses materials available on site, adapted to local environmental conditions, and local labor know-how, which reduces costs. The house also includes smart building features that allow automated monitoring. To prevent possible damages, the owner will also get a user manual for the house. Palm oil is a natural waterproofing used for bamboo pieces. It is available locally and excessive amounts are not required. To extend the lifetime of the OSB panels in the walls, a water-resistant stucco coating is applied. A reflective paint coating is applied on the roof, reflecting radiation, improving thermal and acoustic properties, and controlling humidity. The chart resumes the lifetime and optimal maintenance time of the main materials. All the advantages of Funnel House are monitored by a smart building system to maintain optimal performance. The smart devices can be controlled with a smartphone and keep track of consumption data for optimization. Doors and windows can be also monitored to prevent air leaks. This system alerts neighbors or family members in an emergency. Funnel House conception included its life cycle analysis to minimize environmental impact. Circularity and the value chain were determined, resulting in a material recovery of 151%. Bamboo has a great potential of recovery since it can be renewed, reused, or processed to produce other materials. Deconstruction or selective demolition of the structure is also possible, ensuring maximum recovery of all materials and components. The design was capable of reducing embodied carbon to a minimum, concentrated in structural materials and replacement, achieving a B score. Solar Decathlon meant for us an amazing personal and professional growing experience. We are very thankful for being part of it. It was our pleasure to share with you this design journey, leading to the creation of Funnel House, a plus energy dwelling designed to satisfy its users' desire for comfort and modern quality life, respecting local knowledge, traditional lifestyle, and helping to protect the Amazon rainforest.